Today we're going to talk about monoid objects in monoidal categories. Now, this is a story, one of the usual stories of category theory, where we take something that we know and love and that we're very familiar with, such as a monoid, and we look at it and say, well, we did monoids in the category of sets and functions, basically. Could we try and do it in any other category? And so the first thing we have to do is re-express the original definition just using the objects and morphisms of the category of sets. And once we've done that, we can then just pick it up and plonk it in some other categories, as long as we've got enough features of the category that we're looking for. So in the case of monoids, what we're going to see is that we use the category of sets and functions together with the Cartesian product in that category, in the category of sets. And so we can do this in any category that's got something a bit like a Cartesian product. In fact, we don't need it to be a Cartesian product, we just need it to be a monoidal category structure. So this is what we're going to look at, monoid objects in other monoidal categories other than the category of sets and functions. So first of all, let's remind ourselves what a monoid is. A monoid is a set equipped with, so we better call this set something, it's a set, let's call it A, equipped with, well, it's got a binary operation which we might write as things like, for every A and B, we have an A composed with B like that. So for all A and B in A, we have some element A, B, and A. We also have a unit object, so we have a unit which we could call E, which is an object of A, and then we have associativity and unit axioms. So we've got for all A, B, and C in A, B, C equals A, B, C, and also for all A in A, E composed with A, E multiplied by A equals A equals A, E. So now let's try and re-express this. You see, all over the place we've used elements of this set. And if we're going to do it in some arbitrary other category, we've just got to use objects and morphisms of the category. So what we're going to have here, what we've got is a set A, that's fine. This is an object of our category of sets and functions. So our binary operation, we could express it as something from, it's a morphism, a function from A cross A to A. Okay, so here we define it as something that takes a pair A, B and goes to A multiplied by B. But fundamentally, it's just a function A cross A to A. So you see we're using the Cartesian product here. Now what about this unit? We've got to pick out an object of A. Well, we can do that by specifying a function from the terminal set to A. Because what does a function from the terminal set to A do? Well, there's only one object in here, so all it does is it picks out an object in there. And now we've got to have the associativity and unit laws. Well, we can express the associativity law like this. We've got to take three elements, right? So that's going to be something in A cross A cross A. Let's call this multiplication mu. Then what we've got to do is we've got to multiply first on the left and leave the right-hand side one alone. And this takes us just to A cross A, okay? And then we're going to do mu on there, and that takes us down to A. Down the other side, we could have done mu on the right, and then mu afterwards. So here we're taking a triple, A, comma, B, comma, C, and we're sending it to A times B, comma, C, and then finally we're sending it to A, B, C, and down the other side we're doing it the other way. So finally we've got this unit axiom, and I didn't quite leave myself enough space over there, so I'll come over here. This unit axiom says, well, what have we got to do here? We've got to pick out E and an A. So what that says is if we start with 1 cross A, we can use our unit map to pick out our element E in here, and then we multiply and we get back down to A. And that's canonically isomorphic to just A, and this should be the same thing coming down here. So on the right hand side, we've got something very similar. We've got A cross 1 being isomorphic to A. Here we do 1 cross with eta. So what that does is it picks out in here little a, comma, e, because the right-hand side takes 1, the terminal set, and sends it to e, and that's got to be the same as doing the identity there. So now we can just take this definition and put it in some other monoidal category and give ourselves the notion of a monoid object. So let's wipe this part out. So a monoid object in a monoidal category C is an object A equipped with one cells, that is morphisms, those two morphisms. So we've got to have something from 1 to A called eta, and we've got to have something from A tensor A to A called mu. And then it's got to satisfy our two axioms. Satisfying associativity and unit axioms. Of course, if this isn't a strict monoidal category, then we're going to have to insert some associators in there. So let's wipe this off. No, let's not. Let's write it here. So what we're going to have is, on the one hand, A tensor A, we'll have to insert an associativity constraint in here to get ourselves to A tensor A, but then we can do everything exactly as it was before. Of course, I've done it the other way up from that one, which isn't very helpful of me, so perhaps I should do it the other way around. We've got A tensor A being associated that way around to A tensor A, and then when we come along the top here, we can do mu tensor 1, and then mu, and down here we can do 1 tensor mu, and then mu. And so that's what associativity says, and then the unit axiom, we have to do something, it's that thing that I just wiped off. So this gives us the definition of a monoid object in a monoidal category. In the category of sets, it just gives us back the usual definition of a monoid. And what we'll see next time is that if we do this in the monoidal category of monoids, then we'll get a commutative monoid back out again. And that's exactly by the Ekman-Hilton law. So that's what we'll do next time. Today, we're going to show that a monoid object in the monoidal category of monoids is in fact a commutative monoid, which I think is rather exciting, really. So first of all, let's have a look at the monoidal category of monoids. So monoidal category, we show that the category of monoids is a monoidal category under Cartesian product. Which is to say that if we're given a monoid M, then M across M is also a monoid. Given a monoid M, then M cross M is also a monoid. Well, how do we define it? Supposing we've got something A comma B in M cross M, and we want to define a multiplication with A primed comma B primed. Well, what we do is we do it pointwise. So we get out A multiplied by A primed comma B multiplied by B primed. So that's all going to be absolutely fine. So then what does it for this to be a monoid object, for something to be a monoid object in this monoidal category. So what's a monoid object? In monoids? Well, it's got to be, remember, it's got to be an object equipped with a unit and a multiplication. So we've got to have an object, M, i.e. a monoid. Now we've got to have morphisms, that is, well, what are the morphisms in this category? They are monoid morphisms. So we've got to have morphisms eta from 1 to m, and mu from m across m to m, satisfying unit and associativity. So first of all, let's see what this eta and this mu are, shall we? So what does eta do? So eta goes from 1 to m, and it has to be a monoid map. So this here is the monoid, the very trivial monoid, very uninteresting monoid that's just got one object. So all we have to do is pick out an object here. But look, this has to be a monoid map, right? And the one object in this monoid here is, well, it's got to be the unit. So the unit has to go to the unit here. So all we can do is send our one object here to the units of m. So this eta doesn't really give us anything. What about mu? Mu has to go from m cross m to m, and it has to be a monoid map. So supposing we say that this goes from a comma b to something that we'll call a star b, but it also has to be a monoid map. So that says if we take two things and multiply them in here, what it says is that that mu of a comma b composed with c comma d has to equal mu of a comma b composed with mu of c comma d. So let's see what that is. Well, I probably need some more space up here. Mu of a comma b composed with c comma d. Well, remember, we know what the inside is because the inside says composite pointwise. So this is a composed with c comma o. It's a composed with c comma b composed with d. I don't really need these brackets here, do I? It's a composed with c. And so we take mu of that, which says do a composed with c star b composed with d. Very good. So now what about this right-hand side? This is mu of a comma b composed with mu of c comma d. Now mu of a comma b is just a star b, and this is composed with mu of c comma d, which is just c star d. So what this says is that these two are the same, and oh look, it's exactly that thing from the Ekman-Hilton law. Well, fancy that. So this is the exact condition we needed to be able to apply the Ekman-Hilton condition. So we can apply the Ekman-Hilton argument. So what about the unit and associativity conditions here? Well, what that tells us is that it tells us that this mu is unital and associative. And in fact, we didn't have to impose that condition in order to be able to use the Ekman-Hilton argument, because as we showed last time, we can deduce it from the Ekman-Hilton argument. And that's a good thing, because that tells us that this thing that we've defined really does satisfy the unit and associativity axiom that we want. So we get the fact that a monoid object in Mon is precisely